Okay, sorry about the delay. Good afternoon. So let's start our lecture. So we start chapter 4. In this chapter, basically we concentrate on some of the common distributions that we encountered in the real life. And so what we're going to talk about for all these special distributions that we are going to discuss are that, okay, first of all, what does a given random variable represent? What does it mean? All right? And then what kind of distributions can be used to model this random variable or this problem? And we also discuss some of the properties about these distributions. For example, the probability function or the probability density function. Then we also talk about two very important summary of the distribution, the expectation of x and the variance of x. All right? Okay. So to begin with, these are the distributions that we are going to talk about. So first of all, the family of discrete distributions. We are going to discuss about discrete uniform distribution and Bernoulli distribution, and also the binomial distribution, and negative binomial distributions, and as a special case, there's this geometric distribution. A special case of negative binomial distribution is the geometric distribution. And also, Bernoulli distribution is a special case of binomial distribution. Then we also talk about Poisson distribution and some of the link between these distributions. So one link is that we can approximate a binomial distribution using a Poisson approximation. That means we try to approximate a binomial distribution, use a Poisson distribution. So you have to be aware of how we can use, or how these two are linked or are related, and also under what conditions that we can use this approximation. All right? Of course, there are other questions, but we are not going to investigate or to address. For example, how good the approximation is. So that is not so easy to answer questions. All right, for continuous distributions, we have this continuous uniform distribution. Oh, we have uniform distribution, one for continuous, one for discrete. Are they the same? Of course, they're not the same, but the idea, all right, are the same. Basically, it's uniform. The word uniform means that it does not depend on the x value. The density of the probability function does not depend on the exact value of the x. All right, so long as the x belongs to the range for which the probability function or probability density function is positive. Then we are going to talk about exponential distribution. The normal distribution. This is a very, very, very important distribution. And you have come across it before. So now let's look at it again. Then we can approximate a binomial distribution using the normal approximation. Using a normal distribution to approximate a binomial distribution. So here, just last slide, we mentioned about using Poisson distribution to approximate a binomial distribution. Now here, we also use a normal distribution to approximate a binomial distribution. So naturally you will ask, compare with these two approximations. So which one should I use? Under what conditions should I use the Poisson approximation, and under what conditions should I use the normal approximation? All right? Okay, so let's begin our journey about these special distributions. So first of all, the discrete uniform distribution. So a random variable x, remember a random variable means that it's a variable, it takes more than one value. For each value, there is a number associated with it, either reflects the probability or the probability density at that point. So the random variable x takes the values x1, x2 up to xk. Just any k values. K is finite. Any k values. And you require equal probability. If it's not equal probability, is it a probability distribution? Is it a distribution? Do I need all the probability? So what it means is that the probability of the random variable equal to x1 and probability of x equal to x2 and so on. All these probabilities are the same. So now my question is, can they be different? So as a distribution, yes, they can be different. But as a uniform distribution, uniform means that it does not depend on the value, so long as it is one of those x1 up to xk. So uniform, discrete uniform distribution has to have equal probability for all these values. Then the next question is, what is this probability? Do we know that? So obviously we know, because we have only k possible values for x, random variable x, so each one should have the same probability, so it's divide 1 by k. So it's 1 over k for each of these probabilities. All right. It seems obvious, right? But you have to understand why. Okay, so equal probability, and why is it 1 over k? Because I have only k possible values, and each has equal probability, and they sum up equal to 1. All right, this one, not mentioned here, but we mentioned it in last 3 chapters. So you have to remember that. All right, sum of all the probabilities over all possible values of the random variable has to be 1 for discrete case. So we say that x have a discrete uniform distribution, and this is the probability function. All right. Now, usually we just write it like that, but to be complete, we better describe that this equal to 0 otherwise. Otherwise means that if x takes the value other than this x1 up to xk, then the probability function is equal to 0. So in fact, we know all the possible, the f of x for any values. If it's not one of those xi's mentioned here, then the probability function is equal to 0. Okay, so I told you many times that once you know the distribution, that means you know everything about this random variable. But knowing everything may be too much. So sometimes we want to summarize the behavior of this distribution. So these two quantities, the expectation and the variance, are the two that tell us something about the distribution. So the expectation of x, by definition, is x times the f of x times the corresponding probability and sum over all possible x. So in this example, it's equal to sum of all the xi divided by k, or 1 over k times times the sum of the xi. Then for the variance of x, all right, so I just have x minus mu. All right, this one from the definition is the expectation of x minus mu square. All right, so, and we also have just computed this is equal to 1 over k summation xi. All right, so So this is the follow from the definition. This is a computational formula. Recall that variance of x, which is defined as the expectation of this quantity, x minus mu, the whole thing squared, which you can show that this is equal to expectation of x squared minus the square of the expectation. All right. So I just apply that. So you have to know why it's like that. This, in fact, is the quantity x squared times the probability, which probability f of x, which is 1 over k. But each term has 1 over k, so I bring it out as a common factor. So it becomes 1 over k times the sum of xi squared. All right, so these are the variants. So let's look at this example. So suppose I have this a box containing 4 light bulbs. They each have different voltage, different watt. Sorry. So we select one at random. So in this case, each of these light bulbs has equal chance being selected, which means 1/4, and the value are 40, 60, 75, and 100. These are the corresponding watts, how bright your light bulb is. So you can describe it using a probability function, f of x equal to 1/4, where x equal to 40, 60, 75, and 100, and 0 otherwise. All right? And we have another example. We toss a die. All right. So these are the possible outcomes, and they're equally likely, so it's 1/6 for each one. So this, again, is a discrete uniform distribution. How about tossing a coin? Can we describe it by a discrete uniform distribution? How many possible values? 2. What are these 2 values? Okay. Any 2 values. Usually we put it 0, 1. All right? So head map to 1, tail map to 0. So we have 2 values. All right? And then the probabilities are equal if it's a fair coin. So each value, x equal to 1 with a probability half, x equal to 0, the probability equal to half. Can I map head to 2 and then tail to 0? Can, right? Then why people want to map to 1 and 0? Easier. This is not a good answer, right? Because, okay, you can think of it like this. All right? Now, why I map it to 1 and 0, not 2 and 0? All right? Suppose a head map to 1. Why not map head to 2? Okay? Now, let's go back one step. Okay? So what is the probability of x equal to 1? It means that it's probability of the outcome of your tossing the coin is a head, right? So, in other words, probability of x equal to 1 means that it's the chance getting a head. Let's say head is a success. So if you get a head, you got a success. So probability of x equal to 1 means the probability of a success. All right? Correct or not? Now I move on to talk about expectation of x. So what is expectation of x? If x map to 1 and 0 with probability half, or p, probability, okay, maybe let me write it down. All right? I just want you to appreciate these kind of things. So now I have x takes 1 or 0. Depends on the outcome, whether it's a head or tail. All right? So, the question is, can I map it instead of 1, map it to 2? The answer is yes. All right? Yes. All right. But why we map to 1? There's some reason why we want to map it to 1. All right, so the probability f of x, that means the probability x equal to 0, let's say it's a fair coin, it's half. Let me make it more general. Getting a head with probability p, then what is the chance of getting a tail? Don't know. What is the chance getting a tail? If the chance getting a head is a p, don't guess. Remember, the probability add up equal to 1, and there are only 2 possible values. So what number at p equal to 1? P plus p equal to 1. 1 minus p plus p cancel, so it's equal to p equal to 1, right? Okay, now how to get the expectation of x? Right? How to get the expectation of x? The value 0 times the corresponding probability 1 minus p. Then another value. What's another value? 1. What is the chance? P. Right? Any other values? No more, because this only takes 2 values. It is still a random variable because it takes 2 values. More than 1 value. If one value is not a variable. So this is equal to what? Equal to 0, equal to 1, equal to p. P. Okay. P. Now, so the expectation of x equal to p. And what is p? Remember what is p? P is the probability of getting x equal to 1. Or if x equal to 1 is considered as a head, and head is considered success, so p is the probability of success. So in other words, the expectation of x is equal to the chance of success, or getting a head in this case. Now, if you use 2, map it to 0 and 2, will you have such thing? No, it will be 2p. Okay, it will be 2p, right? So it's not the probability of a success. It's 2 times p. So 0, 1, these 2 numbers, I remember. Okay, next time when you do a lot of other mathematics problem, 0 is a very beautiful number. 1 is also a very beautiful number. So put this 0 and 1 together. You know 0 is a wonderful number. How wonderful it is. Any number, add to 0, you get back what? Itself, right? That is called additive identity if you learn some linear algebra. How about 1? Any number add 1 will not equal to itself. Right? But 1 times the number, what do you get? You'll get back itself. So it's called multiplicative identity. So these are the 2 numbers, magic number, not others, 0 and 1. Under addition 0 is very beautiful, under multiplication 1 is very beautiful. So this is why we choose 0 and 1 for this, not 0 and 2. All right? It's nothing wrong if you choose 0 and 2, but then it does not help you to expand your interpretation. All right? Okay, so in this case, it's a die, 1, 2, 3, 4, 5, 6, each has 1, 6. So this is the probability function, and 0 otherwise. And the mean is 3.5. All right, if you expect the average is 3.5. Now I just want to highlight one thing. Unfortunately, I start with a discrete uniform. Mean, all right, throw away your definition, sum up all the numbers, divide by the number of observations. That is not a general formula. The general formula for mean or expectation is a weighted average. Each value have to weight by the corresponding probability of occurrence. All right? A very special case is that the occurrence probability are the same. Like in this case, each outcome has 1/6 probability. So it looks as if you just sum up all the number, divide by 6. All right? That is not the general formula. The general formula is x times the corresponding probability of x, equal to that value. Remember that, Okay, similarly, we work out the variance. X minus mu square. So for each value, we calculate it and multiply the corresponding probability, which is 1 over 6. So the variance is 35 over 12. Of course, we can use this formula and get the same answer. If you use the alternate formula and get a different answer, all right, then there are two possibilities. You make a mistake in computation, or you understand wrongly, use the wrong formula. These two formulas, we have got two formulas. So the first one, follow from the definition, variance is equal to the expectation of x minus mu squared. The other formula is after some algebra, we simplified it, it's like this. And these two should be the same. If you got the different answers, you make a mistake in your computations, or you apply the formula wrongly. Oh. Now, binomial distribution is very, very important distribution as well. Okay, before we talk about binomial distribution, we talk about this Bernoulli distribution. So, we start with something called experiment. So, related to some real-life examples. Then, okay, so this experiment consists of two outcomes, failure and success. All right? So, this is very important. It makes life much, much easier because we try to divide what we see into success and failure. Of course, you define success may be different from the common sense of success. All right? So it just success means that the event occur, or the event that you are interested in occur. So suppose I want to find out what is the a success considered as getting a mark less than 20. It's not that easy to get a mark less than 20. So a success is very hard to get. All right, I define success as like getting a mark less than 20. Right? Usually people would think that if I succeed, I should have a high mark. I score 100 marks or 95 marks out of 100 is considered success. But I can define my success as less than 20 marks as a success. All right? So in that sense, success, okay, is just the event that I'm interested that occurs that I consider as a success. So for those who are not complement of it, then it's considered as failure. All right? So we call this a process a dichotomized process. So toss a die, we have 6 outcomes. But then I can dichotomize it as, okay, getting a 1, and then the rest. The rest is non-ones. All right? Or I'm getting odd numbers, that's one event, and even numbers as a failure. Or getting a number less or equal to 2 as a success, and those above 2 is considered as a failure. So it depends on how you define your success. So naturally, it's easier to just define 1 and 0. 1 for success and 0 for failure. We just recode it. All right? So then the probability function of this random variable, which takes the value, basically it's like this. Okay? X takes 2 values, 0 and 1. The probability takes 1 minus p or p. Okay, this is to present the probability function in a table form. All right? But if possible, you can also think of how to express it in a formula, in a closed form formula. So in this case, f of x is equal to p, where x equal to 1. So how to make it where x equal to 1, this one is equal to p. And where x equal to 0, then this is equal to 1 minus p. Now, so this is a mathematical skill that you may have to learn. So I just write it like this. When x equal to 1, then I have a p here. But this one is still there. How can I get rid of it? So here's the trick. 2 power 1 minus x. So when x equal to 1, the power becomes 0. Any number raised to power 0 becomes 0. Right? Huh? Only one say there is 1. What is this? 1, thank you. 1. Any number raised to power 0 is 1. Okay, not 0, huh? Don't. So this one, when x equal to 1, this term is not 0, huh? Oh, yeah, right? It's 1 minus p raised to power 0. It means it's 1. All right? So, in this case, you have p to power x. How about when x equal to 0? When x equal to 0, then this is p to power 0, it is 1. Then this one, 1 minus 0, so it's 1 minus p. So this will equal to 1 minus p when x equal to 0. Then let me ask you, how about when x equal to 0.5? Huh? 0.5. Yeah, it's a tricky question. I cannot use this formula. Hey, x either 1 or 0. What is 1.5? What's the chance getting 1.5? Or 0.5, sorry, 0.5. What's the chance? 0 chance. So, this value only for x equals 0 and 1. And 0 otherwise. All right? So, this is important. You must, I already told you in chapter 3. So, this formula only valid when x equals 0 and 1. And other than that, the probability function is 0. All right? Okay? And also, I specified that P, we call this, we have a name for it, we call it parameter. Or what does this parameter mean? It means that this distribution, or Bernoulli distribution, in fact, not one of them. How many of them are there? Infinite number of them. Because the P can take any values, so long as it is between 0 and 1. All right? So it's a class or a collection of many Bernoulli distributions with different P. But X, for particular distribution, that means a particular P, there are only one distribution. All right? And there are only two values, 0 and 1. For X. All right? So this P is a constant. This P is a constant. Do we know this P? In general, we don't know. All right? Later on, when we talk about statistic inference, we try to collect some data and try to infer what the P value is. Like, let's say P is the probability of getting a hat. X equal to 1, 1 is when we got a hat. So maybe you usually think, oh, it must be a fair coin, so P must be 1/2. But I may have a coin which is not fair. All right? So I don't know what it is. What's the chance of getting a hat? So I tossed the coin 100 times. I got 100 hats. So what do you think? So most likely, the chance of getting a hat is close to 1. That's why you get 100 hats out of 100 tosses. All right? So we'll try to infer the P when by getting some data. All right? But at this point, we assume P is fixed. We may not know. Yeah. Don't watch the video. All right. Okay. So we assume that P is fixed, is a constant, and X is the random variable. All right? So sometimes 1 minus P is denoted by Q. All right? So f of x depends on this quantity p, and this p is called parameter. So remember, in the subsequent discussion, we talk about distribution. So we talk about the probability density function or probability function. In it, there will be this x, the value of x, and also the corresponding probability. And there may be some other unknown constants or some constants which may not know the value. So there are some constants, and these constants are called parameters. So in just the example just shown, that Bernoulli distribution, the parameter is p. P is the unknown parameter. All right? So this collection of all probability distribution of different values of the parameter is called the family of the probability distribution. The same family. That means they are belonging to the Bernoulli distribution family. Okay, so the expectation is equal to P, and the variance is equal to P times 1 minus P. This is a very simple exercise. You only have two values. So this one equal to 0 times 1 minus P plus 1 times P, right? This one equal to 0 minus P, because this is equal to P. So 0 minus P square times what? Times the probability, 1 minus P, plus the other value is 1, minus the mean square times the probability is P, right? So simplified it, so it's P times minus P. So here we have P from this, and the rest I have 1 minus P. Oh, so it's P 1 minus P. Simple exercise, you do it yourself, don't copy. All right. Alternatively, we can work on the expectation of x squared. So it's 0 squared times 1 minus P plus 1 squared times P. So what do we get? P, right? So what is the variance? So expectation of x squared equal P, expectation of x also equal P. So does it mean that the variance of x equal to 0? Both are P. No. Variance of x is not the difference between expectation of x squared and the expectation of x. Variance of x is equal to this minus the square of the expectation. This is P. And this one, P squared. So P minus P squared. Take the P out as a common factor. So it's P times 1 minus P. This one is easier to obtain or to compute. You better practice it yourself. So make sure that you know how to get the expectation of x, how to get the expectation of x squared, and how to get the variance of x. This is the easiest practice because only two values. If I give you three values, you have more computation to do. So my point is that you have to know how to obtain all this from the definition. All right. Okay. So here's an example. What got Q there? What is Q? Just call this 1 minus P as Q. All right. So it's just another way to write 1 minus P is too troublesome. You have two terms. You have to write 3 letters. So write Q, 1. So yes, in practice, a lot of times that in probability, we use P to represent the probability of success. So 1 minus P is the probability of failure. So we use Q. P, Q, R, right? P, Q after R, P. So we use Q to represent 1 minus P. All right. But if no one mentioned it, don't assume that Q equal to 1 minus P. But in probability, most of the time we use Q to represent to denote 1 minus P. All right? Okay, so now we have a box that have 4 blue balls and 6 red balls, and I take only one ball. Take one ball. Okay, what's the probability that a blue ball is chosen? So in this example, we consider a success if we get a blue ball. So the success is equivalent to a blue ball is drawn from the box. So here I define x equal 1 means a success. All right? X takes the value 1. I don't know whether I mentioned it before. Random variables usually is a variable, so we talk about numerical values. So I just answered the question, can I map it to 2 and 0 instead of 1 and 0? So we try to map to 1 and 0 to make all this easier to interpret. All right. So now I let x takes 2 value. 1 means that it takes a blue ball, and 0 means a non-blue ball is chosen. Okay, these are all follow from chapters 1, 2, and 3. In fact, 2. Basically, we have an experiment to take one ball out of the box of 10 balls. All right? And the outcome can be one of these 10 balls. But we are interested in only the color, whether the ball drawn out is a blue ball. So there are only 2 possible outcomes, blue or red. All right? In fact, I can make it a little bit harder. The box containing 4 blue balls, 3 red balls, and 3 black balls. So 3 colors. But I still interested in drawing a blue ball. So in that case, I don't care whether the other color is a red ball or a black ball. I just consider it non-blue ball. So you have to learn this skill. All right? I'm just interested in blue, so I look at blue. The others, colorblind, so long as it's not blue. Okay, it doesn't matter whether it's red or black. All right? But here I specify that it's only blue and red. Okay, so now I define my random variable x equal to 1 when it's a blue ball, and x equals 0 when it's a non-blue ball. And then the next question is, what is the probability of x equal to 1? So it's 0.4. And x equal to 0 is 0.6. So therefore, the PDF is given in this form. So this is another way to write out the PDF. In fact, this is not complete. You should also put 0 otherwise, so that it covers any other x value besides x equal to 0 and x equal to 1. All right? So put back maybe 0 otherwise. All right? Oh, sorry, I put it here. I should move to the next line. All right, to make it complete. All right? Okay, here's another example. Now, in this example, we consider not just one Brownian trials, Brownian experiments, we consider a sequence of Brownian experiments. So each one will either be a success or failure. All right? And let's say the probability of success is P. All right? And they are the same for all the trials. All right? So here is an example. I go back to this box containing 4 blue and 6 red balls, and I draw 5 balls from this box randomly, one at a time, and with replacement. All right? So that means I don't grab all the 5 balls at one shot. One at a time. I take one ball out, look at the color, and then what to do? Put it back. This is what we mean by with replacement. That means we put it back. All right, record down the first ball, we draw whether it's a blue ball or non-blue ball. Then now the box, it still have 10 balls, 4 blue and 6 red. And it does not matter what you get in the first ball, what color you get in the first draw. All right? So let the draw of a blue ball be considered as a success. Then we have a 5 consecutive experiment, each considered as a Bernoulli trials. All right, and the probability of success is 0.4. All right, so in this case, I mean the previous example, in this example too, we are talking about 5 balls. All right, so we draw 1 ball out of the box. All right, record down the color, let's say blue, and then put it back to the box, and then draw the ball again, so it may be a blue ball again, all right, and put it back. Maybe the third one also a blue ball, and the fourth one may be a red ball, and then the last one may be a red ball, all right. So it'd be like, maybe like, this is one possible outcomes of all the 5 trials or 5 draws. All right, so now let's consider we have n trials. So these are the outcomes. X1 is a random variable, represent the outcome of the first draw. So X1 can be 1 or 0, depends on the ball, whether it is a blue ball or a red ball. All right? So let X be the number of successes. This is again a very wonderful thing about 1. So I'm saying that X equal to X2. All right? Remember, X1 takes 1 or 0. Depends whether it is a success or failure. X2 takes the value 1 or 0. All right? If it's success, it takes 1. So what is the sum of all this X1 up to Xn? Because it's just 1 and 0. Is it 1 and 0 only for this X1 up to Xn? So the sum of all the X1 up to Xn, basically just count how many 1s are there. Am I right? So suppose n equal to 10, and you see 3 1s there. So that means out of these 10 trials, only 3 successes. So the number of 1s, or the sum, represent the number of 1s. And the number of 1s means number of successes. So X represents the number of successes out of these n trials, the n experiments. Each experiment has only 2 outcomes. All right? This is a very, very important step. X equal to X1 plus X2 up to Xn. All right? So this is example, count the number of success. That means number of 1s. All right? Now for a particular outcome, let's say X of them are 1s and n minus X are 0s. All right? So I just consider for this particular case, the first X are success and the remaining are failure. So I asked, what is the chance that you will have this sequence? That means you have the first X are success and then the rest are failure. All right? So what is the chance that you got a success here? P. What is the success that you got this? Second one is also a success. P again, right? P, right? Can I multiply all this together? Oh, okay, let's continue with this one first. This is 1 minus P. And this is 1 minus P. All right, so getting an F with probability 1 minus P. Getting an S, the probability is P. Now the question is, how can I get all this? X of them are successes, and n minus X are failures. What is the chance? Right? So, for those who like to manipulate the operations, so it's either plus or times, right? Can I add all this? But why? Okay, maybe this is too long a sequence. Let's consider only two sequences. All right? So how do I get S and S? First one is a success. Second is also a success. What is the chance getting this one? What does SS mean? It means that you need both of them. The first one must be a success. At the same time, the second one must be a success. So you need N. I don't know whether you still remember probability of A intercept B. Right? How to get probability of A intercept B? It's probability of A times probability of B given A. That's one way to do it. But we don't know. But there's another one. Probability of A intercept B is equal to probability of A times probability of B. Is it always true? No. When is it true? This magic word. Thank you. Independent. What independent? Probability A intercept B equal probability A times probability B. So yes, independent. So what independent? What are independent? What independent? So you answer this maybe, okay, I close one eye. Okay, you answer partially correct. To be more strict, is the events A and event B are independent events. Then you multiply the two probability to make it equal to the probability A intercept B. So the same applies here. I want the first one as success, the second one as success, so I have to multiply the two probabilities if the first one got a success, is independent of the second one whether it's success or not. So now I ask you, if I take the ball with a blue ball, all right, then what's the chance that the second ball that I draw is also a blue ball? Will it affect it? Why not affecting it? If I take the blue ball out, I keep it in my pocket, then what's the chance that you will get? Well, it's the same. If I draw another ball, which is a red ball, I mean, the first one is a red ball, and then the next one you draw maybe a different probabilities. So this with replacement is very important, because once I draw the ball, I record down, I put it back. So it's just like as the initial state, you have a box with 10 balls, and 4 blue and 6 red balls. So they're independent. So I multiply them. So the chance of getting this X success, then it will be P to power X times 1 minus P n minus X. That is the probability of getting this particular sequence with X successes and n minus X failures. Then how about this one? So, is X, okay, it's still X successes, but this, one of the F is at the second trial. You still have X successes, but this particular sequence gives you X successes and n minus X failures. So what is the probability getting that sequence? I still have X successes, I still have n minus X failures, so the probability of getting this sequence is what? So P times 1 minus P times P times P times 1 minus P and so on. How many 1 minus P are there? N minus X. How many P's are there? X. Because I'm saying that there are X successes and n minus X failures. So in other words, this sequence, this particular sequence, also give me X successes out of n trials, right? I can give you another sequence with X successes, all right? So now my question, how many such sequences that will give me X successes. Headache, right? But we learned it before. All right? It basically, you can think of it like this. You have n numbers. 1 to n. 1, 2, 3, 4, up to n. You just select X number out of it. Right? X numbers. X numbers. How many ways that you can choose out of n distinct objects and choose X of them? What I'm saying is that, okay, I have n objects. These are my n objects. I just select out of these n objects. I pick, let's say I pick 1. Pick 1. All right? Now X equal to 1, to be more specific. X equal to 1. How many ways I can select 1 out of these n objects? Right? So, choose 1 out of n. So this is the number of ways that I can choose. So if I pick you pick the number 1, then that means the first one is a success, the rest are failures. If the number I pick is 3, then that means the third trial is a success, while the rest are failure. So altogether, there are n choose 1 number of sequence that will give me 1 success, and the rest are failures. So now, come back to this. Now I have X successes. How many such sequence? So obviously, I choose X objects, X of these numbers, out of these n numbers. All right? So that is the number of sequence. That will give you X successes. So in other words, if I answer the question, what is the probability the number of success equal to X? X represent the number of successes out of n out of n Bernoulli experiments. So this, all right, a particular sequence has a probability of success equal to this. But this is only one sequence. Altogether, this just one of those sequences that will give me X successes. So how many of them? So this is the one. So this is the probability of getting X successes out of n trials. All right. Yeah, your wonderful graphic calculator can give you this probability. I want you to understand, or at least know, how this formula obtained. So it just basically divide into two parts. First of all, you fix a particular sequence with the number of success fixed. All right? So to make it simple, I just put all the success as the first X, and then the rest failure. So what's the chance of getting this particular sequence? That gives you X successes. So the chance is P to power X times 1 minus P to power n minus 6. We can do that because all these trials are considered as independent. They will not affect the outcome of the others. All right? So it's P to power X times 1 minus P to power n minus X. But the next question is, how many such sequence will give me X successes? So it's choose X numbers out of n numbers. All right. X, or the numbers here represent which one, each location in the sequence that you get a success. All right? So that is the probability. So here, this is answer. And this only valid for X between 0, 1, 2, up to n, and 0 otherwise. All right? In fact, that is a binomial distribution. Okay, so here it is. X is a random variable. It represents the number of successes out of n. And each trial has only two possible outcomes, success and failure. Success and failure. All right? So X represents the number of successes out of n, we call it dichotomous trials, only two outcomes. And in fact, I also should add in another word, adjective, is independent trials. Independent trials. Not only that, the probability of success has to be the same for each trial. That's why in the previous example, I take out the ball. Now, if I don't put back the ball, then the probability of success will change, right? If I take out a blue ball, now I have only 3 blue balls out of 9 balls. But if I take out a red ball, now I still have 4 blue balls out of 9 balls. So the probability change. So that's why in order to maintain equal probability of success, I have to put back the ball. So that's why we consider the problem of independent trials or with replacement. So this is the probability. So this is the value of the random variable. And there's still 2 quantities, the n and the p. These are not the random variable, but it's part of the probability function. So those 2 are called parameters. So in other words, I will try to describe the binomial distribution, many of them, depends on the value of n and p. So n and p's are considered as the parameters. N and p are the parameters. All right? So x equal to 0. Remember, start with 0. You can have, out of these n trials, all fails. So you have 0 successes. Okay? So x starts from 0. X does not start from 1. X starts from 0. Out of n trials, you cannot have n plus 1 successes. So the number of success at most is n. And the minimum is 0. While p is between 0 and 1. And in my expression, I replace 1 minus p by q. Okay, so x, remember, is the number of successes in n independent Bernoulli trial. Bernoulli represents that there are only 2 outcomes. 2 outcomes, success and failure. All right, so in particular, if we don't consider n Bernoulli trials, just 1, then this reduce back to the Bernoulli distribution. Okay, here is a graph. Okay, so this graph, the x-axis are the possible values of x. The vertical axis, the y-axis, represent the probability, or the f of x. All right. This is x followed by binomial with n equal to 10 and p equal to 0.5. This distribution is symmetric. Symmetric about the center. All right. Symmetric means that if you put a mirror at this point, at this location, then the one on the left is just a mirror image of those on the right. All right. Is this symmetric? This part is not symmetric. No matter where you put your mirror, you will not have the image on the left. The bar, the shape of the bars, arrangement of the bars is not the mirror image of the other side. In fact, this we call it skew. A skew has 2 directions: skew to the left or skew to the right. All right. So this one, with x followed by binomial with with n equal to 10 and p equal to 0.5. So this one is skewed to the left or right. Anyone knows that? Skewed to the left or skewed to the right? Right. Skewed to the right. Skewed to the right. Then this one, skewed to the left. Why is it skewed to the right? So there are reasons, okay? But you can think of it like this. If you find your tails on the right-hand side is skewed to the right. Tail. Do you agree that this is a tail? Right? It's a long tail. All right? So if the tail is on the right-hand side, it's skewed to the right. If the tails on the left-hand side is skewed to the left. So you can see that it's very simple. When the P, the probability of success is very high, close to 1, like in the third graph, the P is 0.9. Then you can see that the chance of success is so high, so out of 10 trials, it's likely that you will have a bigger number of success. That's why the probability towards the large X value is big. All right? On the other hand, if the P is equal to 0.2, very small probability of success, then it's most likely your number of success out of 10 trials will be a small number. All right? So that's why the probability is large for those small X value for the first graph. So that's how we interpret the graphs. All right? Okay. So the mean and the variance. So the mean is n times p. The variance n times p times 1 minus p. All right? So, did I show you how to do it? No. There are at least 2 ways to do it. One, follow from the definition. X times the probability of X. Then sum over X from 0 to n. Wow, look at it. How to get this sum? Very hard. All right? For those who are interested, try to look out how to do it. All right? So the variance, it will be X minus the mean. So suppose we got the mean equal to NP, so it's NP square times nx p to power x 1 minus p to power n minus x. Sum. Wow, this is even tougher than the previous one. All right. But let me just give you a little bit the trick that people used in this case. Remember one thing, it's very important. What can we say about this? X. Do you know the sum? Do we know the sum? What is this? This is the probability of X. The random variable X takes the value equal to X, right? And you sum over all the possible values of X. So answer 1. Yes, thank you. This will be used for a lot of the problems. The sum of the probability function is equal to the sum of all this one is equal to 1. So then, just sidetrack. What is this? What is this? Is it equal to 1? Or is it equal to something else? It's very simple. This one, you add one more term. Then it's equal to 1. The whole thing will be equal to 1. What term you add? X equal to 0. The general term, put x equal to 0. I want this one. But then if I add, then it's equal to 1, then this whole thing is equal to 1. Am I right? Can you calculate this one? Right? Easy. So you will get the answer. All right? So this is a trick that you may find it useful. All right? So, but I want to show you an easy way out. Remember two things. Just now I mentioned x equal to x1 plus up to xn. Right? This is the Bernoulli trials. This is a Bernoulli trials. And adding up all this is the number of successes. So, what is this? Is this correct? Is this correct? Expectation of x. If x equal to x1 plus x2 plus x3 plus x up to xn, then expectation of x equal to the sum of the expectation of x1, expectation of x2, expectation of x3, and so on. Is this correct? Revise your notes, chapter 3. We come across this one. What's the expectation of x1? X1 is a Bernoulli distribution. Takes 1 and 0 only, with corresponding probability p and 1 minus p. We just say p, right? P plus p plus p plus up to the last one is still p. How many p's are there? N, no? So it's np. So you see there's another trick. May not apply to others, but then at least for this problem it's np. Right? So the answer is NP. So variance of x, does it equal to this one? We go and flip the note. Let's see whether it's mentioned there. And obviously it's not true in general. There's some other things. Is 2 times covariance of x1, x2 plus 2 times covariance of x1, x3. Wow. I even don't want to write so many. Right? So any two of them, x1, x2, x1, x3, x1, x4, and so on. All right? I had it, so many terms. So you want it to disappear. All right? Maybe your mind is so strong that it disappeared. All right? But you have to tell me the reasons why it disappeared. What's the covariance of x1, x2? Are x1, x2 independent? The outcome of the first one, whether it's success or not, and the outcome of the second trial, the outcome whether it's success or not, they are independent. So therefore, the covariance of all this, x1 or xi, xj, are all zeros. All right? And you cannot just want it to be like that. You must explain why there's no such covariance. Because xi, xj are independent, so they disappear. So what is this? Variance of a Bernoulli distribution. Look at your, just a few pages, maybe. So this is p times 1 minus p. So each of them is p times 1 minus p. So altogether, it is n times p times 1 minus p. It's just an exercise, all right? Okay, so now let's look at some examples. Oh, sorry, conditions for binomial experiment. So it must consist of n Bernoulli trials. Repeat here means that each Bernoulli trials represent the same experiment. All right? It does not mean that all the outcomes are the same. This one helped me to, x1 plus x2. Okay, if x1 is a binomial, is a Bernoulli with p, x2 is a Bernoulli with probability p. Then x1 plus x2 can I write as 2x or 2x1? Because they are of the same distribution, can I do it like that? Let me repeat my question. Maybe you don't understand my question. I have two random variables. X1 follows certain distribution. I make it more specific. Just a Balloonian distribution with parameter p. X2, same distribution, Balloonian distribution of parameter p. They follow the same distribution. So now I want to get the sum x1 plus x2. So my question is, does it equal to 2 times x1? If I say x1 plus x2 equal to 2 times x1, then I simply say that x1 equal to x2. So now my question is, do you believe that x1 equal to x2? How about the random part? What does n? So x1 can be a success. x2 can be a success, can be a failure. How can the x1 equal x2? x1 equal x2 in a sense that they follow the same distribution. Same distribution. It does not mean that the outcome will be the same. All right? So I toss a coin. I toss the coin. Every time I toss a coin, so are they the same? No, the outcome may not be the same. So x1 plus x2 does not equal to 2 times x1, even though x1 and x2 follow the same distribution. They follow the same behavior, but does not mean that the outcome will be the same. You cannot say x1 equal to x2. All right? We only say that x1 and x2 follow the same distribution. If you really say that they have the same random variable follow the same distribution, but the occurrence, the value, is not the same. So cannot multiply 2 times x1. 2 times x1 means that x1 take whatever value, you have to multiply the twice. That means you force x2 to take the same value. It does not make sense for random variable. You mean 2 times x1 means that you get the value of x1, you have to multiply by 2. So that means you imply that the value of x2 is the same as x1, which is not true for random variable x1 and x2. All right, so repeat trials means that they follow the same distribution and only 2 possible outcomes for each trials, and the probability of the success remain the same for each trial. If they are different, then they will not consider as a binomial experiment. And all these trials are independent, which means that the outcome of one trial is not linked to the outcome of the other trials. So the random variable x is the number of successes among the n trials in a binomial experiment. And then we say that x follow a binomial distribution with n and p as parameters. Okay, here's the example. What is the probability of observing exactly 6 heads when an unbiased coin is flipped 10 independent times? It seems redundant, but I don't know, maybe there's some very, very skillful player, they can throw the coin every time got a head. Then it's a different story. So for normal people like us, we cannot. We don't have to toast the coin is either head or tail. So the outcomes are independent. Okay, so now, before you address to this question, you must identify the random variable. So the random variable here is x. We use x. Can I use y? Also, you can use y. Or it's just a name, right? Okay, so x, but the important thing is, what does x mean? So in this case, x means the number of heads. Heads is considered as success. The number of success in 10 trials. And each trial, only 2 outcomes, success or failure. In this case, head or tail. So it's the number of success or number of heads out of 10 tosses. That is my x. So it's the whole thing fulfill the criteria for binomial experiment. So now this basically saying that what is the probability of x equal to 6? Exactly 6. Where x is a binomial distribution, B. Number of trials, 10. Probability of success, half. Why half? Because it's an unbiased con. That means it's a fair con. It does not bias towards it's not biased towards either one. So the chance is half. Okay, so x is the number of heads in 10 independent choices. So this is my n, and this independent, and this is the trials, and this is the number of successes. All right, x denotes the number of successes in n independent by Bernoulli trials. All right, so x follow a binomial distribution with n equal 10 and p equal to 0.5. So the probability is choose 6 out of 10 times probability of success times x, 1 minus p times 10 minus x. All right, where x is equal to 6 and p is equal to half in this question. So this is the answer. You can simplify it and get the answer 0.2051. All right, so if you have a graphic calculator, maybe a piece of cake to get this number. All right, if you don't have a graphic calculator, you may need some help. I mean, you may need this formula, right? And then you just applied it. And the problem is when you ask, for example, if I want to ask change to equal to 6, if I want this, graphic calculator can do that, right? I believe, right? Get this number? Can graphic calculator? I have no experience with graphic calculator. So can graphic calculator got this one? X followed by normal distribution? Oh, you don't know, Okay, so let's find out in the exam, right? Can graphic calculator get this answer right away? Or instead, you have to get probability x equal to 6, x equal to 7, x equal to 8, x equal to 9, x equal to 10, x equal to 11. Do I need x equal to 11? No. How can you have 11 success out of 10 toasts? 11 heads, so it's 0. So beyond that, no. So I just worry. So if you don't have graphic calculator, you may have to add 6, 7, 8, 9, 10, all this probability. Wow, 5 of them. Each one like that. But don't worry, I will help you. So I will provide you with some table that will give you the what we call cumulative probability, right? So it just, for this one, is equal to, right? Equal to this one. Hey, do you remember what is cumulative probability? The CTF? It is from the left-hand side. X, the random variable, x less than certain, so less than 5, less or equal to 5. All right? Okay, so this is, okay, help you to, if I give you the cumulative one, but this sorry, not cumulative, but we call it left-hand tail, so the upper tail of the probability. The CDF is the lower tail, so this is the upper tail. So probability x equal to 6 is equal to the difference between these two probabilities. So these two probabilities will be given in the table, in a table form. All right. Yeah. Okay. So, apart from the exam, if you really want it, Excel have a command for you to calculate the binomial distribution, and there are 4 arguments. 4 arguments. The syntax is binom dot distribution, binomial distribution. The first argument is the x, the value x. Then the second one is the number of trials, n. The third argument is the probability of success. The fourth argument is true or false. If it's true, you put true there, it will give you the cumulative probability up to x. So in other words, if you put true here, okay, this one is false, means that we are computing the probability of x equal to 6. If you put true here, then this is probability of x less than or equal to 6, where x follow a binomial distribution with n equal to 10 and p equal to 0.5. So that's for Excel. All right. Of course, there's another software, I don't know whether you heard about it, R. You can also get this part, so get the right command. And I think does Python also able to get you this? Yeah, can, okay. So, but it will not be tested in the exam. All this will not be tested in the exam, just for you to use it when you want to check your answers. Oh, here is the table that I mentioned. All right? In this table, unfortunately, this table only valid for n equal to 10. All right? N equal to 12, n equal to any other numbers not given in this table. All right? So it gives you the upper tail. That means the probability of x greater or equal to x. So how to read it? So this one, the column heading, all right, referring to the p. P equal to 0.1, 0.15, 0.2, 0.25. And this row heading referring to the x. Referring to the x. So if I want to get the probability of x equal or greater or equal to 6, when p equal to 0.5. So I look at this column and look at this number. Greater or equal to, so it's 0.38. This is the probability of x greater or equal to 6. All right? Yeah. All right. So here is a question. All right. P equal to 0.6. The probability of success equal to 0.6. No 0.6 there. Did I miss out something? I forgot to put P equal to 0.6. So, if this is what you're given, no P equal to 0.6, then you think about it. If P equal to 0.6, P represents the probability of success equal to 0.6. Can I swap the events of success and failure? Right? So, if the probability of success is 0.6, so I change. Now, what you consider as success, I consider as failure. What considered as failure, I consider as success. So now, the probability of success, the new success, will be 0.4. You understand? For example, toss a coin. Head is success. The probability of success is 0.6. All right? So now I consider differently. A success is getting a tail. So the tail, what is the chance that you got a tail? 0.4. 1 minus 0.6. So it's 0.4. All right? So in other words, I want to compute probability of, or the probability of number of heads greater or equal to 6 with probability of success equal to 0.7. All right? Sorry, the table does not provide that. All right? Okay, so what to do? Instead of looking at probability of x greater or equal to 7, I look at probability of y less than 3 or less or equal to 2. Right? What does it mean? Y now becomes the number of tails that I got. Okay, so y is considered as the number of success. Now this time the success is getting a tail. And what's the chance of getting a tail? It's 0.3, right? Oh, okay, I mixed up. So probability of success is 0.7 for head. So probability of getting a tail will be 0.3. So now I have 0.3 there. But also I have to change the statement. x greater or equal to 6. Now I change to y less or equal to 3, right? Because x equal to 6, 7, 8, 9, 10. Okay. Then I change to y. It becomes what? 1, 2, 3, 4, 5. All right. Sorry, 0, 1, 2, 3, 4, 5. All right. So my point is, if you are given something that is not so explicit, you have to think of a way to work it out. So this one is very simple. You just swap. You define a success differently. All right? Change. The original one, the success now becomes failure. So like head is a success, now I call tail a success and work accordingly. All right? So that's how you do it. So example 2, probability of child recovers from certain disease is 0.2. 20 children contract this disease. What is the probability of getting at least 8? So X is the number of children out of 20. So I specify the number of occurrence. Occurrence is recover from the disease as considered success. Number of success, that means number of children recover from the disease out of 20 trials. And X follow a binomial distribution with n equal 20 and p equal to 0.2. And we are looking at probability x greater or equal to 8. And x between 2 and 5. So which turned out to be 0.735. This is 0.032. All these are reading from the table with n equal to 20. Oh. So I change another table, n equal to 20. All right. Is it the same table? Okay. Give me 2 or 3 more minutes. Let me finish this interesting problem. So this man claimed that he is special. He has this extrasensory perception. All right. And then he said that he can predict how many heads. He can get many success. So a success is considered getting. He can predict the outcome of in advance. All right. So okay. If it's not just predict, he can get a lot of living. Any other got exams? Okay. Okay, maybe I save this to next week. Not next week. Today is Tuesday, right? We still have one more meeting, right? Okay, let's save this to Thursday. All right. So, in fact, I also want to ask you, if I have 100 numbers, 1 to 100. All right. So I want to get a large number. Is 95 considered large? Right. Okay. What's the chance I got a large number? Okay. My point is that when you are saying that it's a large number, you cannot just look at the value. You have to look at the probability of getting some other numbers that is bigger than yours. So suppose your test, you got 99 marks out of 100. Very good, right? But sorry, you are the only one who got 99 marks. The rest of the class got 100. After all, you are not that big, not that great, right? So you are looking at how many, what's the chance that people will do better than you do. That's considered good, right? 99. In fact, I say that 99 is good. But then when we conclude whether you are good or not in the class, you are compared with the others. So like when I ask you 1 to 100 numbers, which one is the best, which one is larger? Drawing 50, what's the chance getting a 50 out of this 100 number? 1 over 100. What's the chance you get 100? It's still 1 over 100. But obviously to us, 100 seems to be a very large number. Right? So you ask this question. What is the chance that you get a number bigger or equal to what you get? 100. What's the chance that you get some number greater or equal to what you get? 1 over 100. What's the chance that you get a number greater or equal to 95? 6 over 100. 95, 96, up to 100. What is the chance that you got 51? The chance is quite big. Half of the chance. So 51 is not that big. 100 is considered big because the chance that you get something more than what you see is small chance. So you got a big number. All right? So you cannot just look at the magnitude. That's my point. So we'll bring this up again in this example 3. All right? So we'll repeat this again in Thursday lecture. This example. All right? Yes. So see you next lecture. It's getting smaller and fewer and fewer. Maybe this because of the exam, the midterm test week. I hope after Thursday, right? All the midterm tests are already over and see more of you here. Those who are watching webcasts especially.